Hello everybody. This is going to be the last chapter in the course that we teach here at KFUPM. Um, there are other things or topics that I'm going to cover after this chapter. This is not something we cover in this course, but these are things that I used to teach in another place that I was teaching before, and I thought it's going to be useful to include these parts in this same course, just to make it more useful for everybody. So this chapter has the title of Differential Analysis of Fluid Flow, and I'd like to keep this first video as an introduction to this chapter, and this is going to for what I see that this is going to be a very important introduction. I don't think it's well introduced in the textbook, or it may be well introduced, but for me it's not enough. That's why I want to like give some examples just to clarify why we need this chapter, or why we're going to discuss this chapter, and also to give kind of like an introduction to what type of equations we're going to use in this chapter. So the previous chapters that we covered in this textbook, including the fluid statics and dynamics, within in chapters 5, 6, 7, and 8, and also in the packed and fluidized beds part that we just covered before, we dealt with the fluid as a whole, meaning that we had the pipe with a velocity profile, that the velocity is 0 at the sides and maximum at the center, and we did the calculations for the kinetic energy, for the velocity in the continuity equation, for whatever as equation that we needed the velocity as the average velocity. And we said that the average velocity can be a good approximation that will express the whole fluid in the whole pipe or tube. And this was very useful, and it was a very good approximation that we used to calculate what we wanted to calculate, whether the pressure drop, the velocity, or whatever, in an easy and straightforward way. However, this is not going to be useful for all the cases, meaning that there are some applications that require more details about the fluid flow. Meaning that we need to know the velocity at specific points in the flow, we need to know the pressure at specific points in the flow, the shear stresses at specific points of the flow, and this is not something that the equations that we used before, whether it's Bernoulli equation or the modified Bernoulli equation, the continuity equation, they cannot serve in this case. Examples, I'm going to give like 4 examples, and I hope these 4 examples are good enough to clarify the point I want to discuss here. So let's say we want to design a pump. This is a pump for your information. This is a shape of a pump, and you want to design it and choose the material of construction, to choose the thickness of the pump so that it can withstand the pressure inside. And you want to do this in an efficient way, so you don't use more materials in a part than needed, or less materials in a part than needed, I mean thickness than needed. So you need to know what is the velocity and the pressure, or mainly the pressure, at each part of the each point of the fluid inside the pump. And you also need the velocity, because this will let you know how much friction that will happen, and how much or what material that can be used to withstand this friction. So you cannot use Bernoulli equation in this case. You cannot use the simple form of the continuity equation that we used before. You need to know the pressure and the velocity at specific points in the flow, and this is something that these equations cannot help with. The second example that we see here is the race cars. So you can see the race cars have designs that are very different from the designs of regular cars or trucks. And the reason is that this design is very specific, because the cars are running at very high speed, and the air velocity or the air resistance can be very high in this case. So the design is made to make the air resistance as minimum as possible. And you see there are some places for the air to just go in and out, so it's not part of the engine or something. It's just to make the airflow as smooth as possible. So we need to know also the velocity at specific points, or at each point. We need to know the pressure of the air at each point, so we can make the design accordingly. Bernoulli equation and the equations we used before cannot help with this. One other example. It's a very interesting one here that has to do with the ventilation systems or air conditioning systems. So and this is very important in case of having people who are sick, or it might be very important in hospitals, or in places where there are like harmful fumes that need or to not be distributed in the place. So the airflow can be studied to know exactly what is the velocity and the direction of the air at specific points in the or different points in the room, and whether if this virus or whatever thing will be spreaded in the whole area or the whole volume or not. And this is something that requires a tool or a way to study the velocity at different points, and how the air velocity and direction varies from point to another. The last example that I have here is the design of tall buildings. So when you have a building that is tall, let's say more than 10 meters or something, the velocity of air at the high altitudes is higher than the velocity of air at lower altitudes, and this velocity will lead to a lot of stresses on the building, and therefore we need to know how much stress we expect, and based on this we can design the building accordingly. There are types of vessels in chemical engineering that we design. If they exceed like the distillation columns, the reactors, if they exceed a specific height or length, they are considered tall buildings. And on the design of these tall buildings, we take into account what we call wind load, which is the stresses due to the wind, due to this high altitude. So this requires knowledge of the velocity at different points, and accordingly we can know how to design this building. So the take-home message of all these examples that I just gave here is that the equations that we have been using will not serve to answer these questions or to help us calculate what we want to calculate, and this is why we need new types of equations or more detailed equations. It's going to be the same categories of equations, like the conservation of mass and energy, but it's different different form of equation or more detailed form of equation that we can use to help us calculate what we want. What we would expect that since we are looking for more details, then the equations would be more complicated, and this is something you need to be prepared for, that the equations that we are going to deal with are going to be much more complicated than what we used to see before, although they are the same categories, as I said, the conservation of mass and energy, but they're going to be more complicated. And also we need to be prepared that the equations would be derived for differential elements. Since the velocity and the pressure are going to vary from a point to another, then the elements are going to be differential elements, or the equation can be applied first to the differential element. And this is something we discussed many times before. Why do we start with deriving the equations on a differential element? And we said that the parameter is going to change from point to another, so we have to take a very small element. We consider the properties are constant in this element, and then we can integrate over the whole volume or the whole area. So this is something we need to be prepared for. The equations we are going to use are differential equations, and they are not ordinary, they are partial differential equations. So this is like a point that has to be taken into account, or to prepare yourself for this, because I know the differential equations are not something that most people like to deal with. We will see how to deal with these equations and whether we can solve them manually or we have to use a software, and what are the cases that we can deal with manually and what cases that we need to use a software to deal with. And this is something we will discuss later. But for now, just be prepared that the equations we are going to use are differential equations. And also, since we are interested in the directions of the flow, they are going to be vector equations. So these are two things that have to be part of the equations. We can expect this. So starting next video, I'm going to give a quick review on the basic vector operations that we need to remember before we go through the equations, and then we will see what are the equations that we're going to use. So I'll see you then, inshallah. Goodbye.